These are cards from a wonderful game called Set, which I'll explain in a moment. And these are 3 cards that form a special pattern, also called a set. When playing the game, we're always hunting for such patterns. But sometimes there are no sets. That raises the question, what's the largest number of cards you can have without any sets? In this video, we'll answer that question. It's not just a party puzzle. Top mathematicians such as Terry Tao have studied this problem in higher dimensions. In 2007, he called high-dimensional set perhaps his favorite open question. In 2016, there was a breakthrough in high-dimensional set. It's still not fully solved. In this video, we'll crack the problem in 2 dimensions, 3 dimensions, and 4 dimensions. Along the way, we'll use elegant concepts that you might see in a course on combinatorics or discrete math. I've also created some set exercises for you to explore on your own. Near the end, I'll tell you what's known and unknown about the higher dimensional versions. Are you ready? Let's go! Here's a set card. How would you describe it? Well, it contains a shape, a squiggle. 3 of them. They're purple. Finally, the squiggles are shaded with stripes. We can describe every set card using these 4 features. Each of the 4 features has 3 choices. So how many different set cards are there? Well, we can multiply 3 for shape, 3 for number, 3 for color, and 3 for shading. The product is 3 to the 4th power, which is 81. Set has 81 cards. Here they are. Set was invented by Marcia Falco in 1974. She was a geneticist who represented each dog she was studying with a card, looking for patterns among the cards. She decided to make a game out of the cards, and what a fun game it is. So far, we looked at 1 card at a time, but in the actual game, we look at several cards at the same time. For example, let's add a 2nd card. I've placed check marks for it. Let's add a 3rd card. These 3 cards form an interesting pattern. They have all different shapes, the same number, the same color, and all different shadings. We'll give a name to such a pattern. We'll call it a set. A set is a collection of 3 cards that satisfy 4 conditions. The 3 cards either have the same shape or all different shapes. The cards either have the same number of shapes or all different. The colors are the same or all different. The shadings are the same or all different. For example, do these 3 cards form a set? Let's mark a chart as before. Here are the marks for the 1st card, and the 2nd card, and the 3rd card. The shapes are the same, the numbers are the same, and the colors are all different. So far, so good. But the shading is off. We have 2 empty shadings and 1 solid shading, so we don't have a set. Whenever some choice appears exactly twice, the 3 cards don't form a set. How about these 3 cards? The shapes are all different, the numbers are all different, the colors are all different, and the shadings are the same. So yes, we have a set. Let me ask you a mystery question. Suppose we have these 2 cards. Can you find a 3rd card that makes a set with them? Let's make a chart again. Here are the marks for the 1st card and the 2nd card. For the shape, we want all the cards to be different, so the 3rd card should be an oval. The number should be different, so 2 ovals. The color should be red. Finally, the shading should be solid. We found the mystery card. No matter which pair of cards we start with, we can always find a unique 3rd card to make a set. We'll use that uniqueness principle later. So, how do you play set? One player places 12 cards on the table. Let's say you find a set like this one. Then you keep those 3 cards. Those cards are replaced by 3 new ones. What happens if there are no sets? Then 3 more cards are added. So 15 cards are on the table. What happens if there are still no sets? Then we add 3 more cards. That raises a question. What's the largest number of cards you can have without any sets? Here are the 81 cards again. What's the largest number of them you can choose without any sets? That's a lot of possibilities to check. At this point, let's follow the problem-solving advice of the mathematician George Polya. He said that if you can't solve a problem, find an easier related problem. After you solve the easier problem, you can go back to the original problem. Okay, how can we make the problem easier? Set has 4 features, 4 dimensions. We can ignore one of the features. Actually, the company that makes Set already markets a 3-feature game. It's called Set Mini. All the cards have solid shading, so only the 3 other features are relevant. How many cards does Set Mini have? It has 27 cards, namely 3 to the 3rd power. Here they are. Set Mini is easier, but still not easy enough. Let's further restrict to the red cards, say. That gives us a 2-dimensional game with only 9 cards. Of these 9 cards, what's the most cards we can choose without any sets? Feel free to pause the video to try that question. I can find 4 cards without a set. Here's my example. You might have a different example. We still have to prove that 4 cards is the maximum without a set. Let's try a proof. I'll start with my 4 cards. No matter which 5th card I add, there'll be a set. Does that prove that 4 is the maximum? No, that proof is bogus. All it proves is that my 4 cards can't be extended. How do we know there isn't some completely different way of finding 5 cards without a set? The maximum is 4 cards, but we'll need another proof method. We'll prove that 5 cards must have a set. The proof will be by contradiction. Assume we have 5 cards without a set. We'll eventually reach a contradiction, which means there weren't 5 such cards. As Sherlock Holmes said, when you've eliminated the impossible, whatever remains must be the truth. How shall we proceed? So far, we know only one math principle for set. Namely, if we have a pair of cards, then there's exactly one set that contains both cards. Let's try to use that uniqueness principle. This principle is about a pair of cards. Among our 5 cards, how many pairs are there? We can draw a graph of all the pairs. There are 10 edges, 10 pairs. We can also compute the number of pairs using a binomial coefficient. 5 choose 2 is 5 times 4 over 2, which is 10. We'll next count the number of pairs in another way. That seems like a weird thing to do, but it's an important tool in combinatorics. It's called double counting, or counting in 2 ways. The 2 counts should give the same answer. If we get a different answer, then we'll have a contradiction. To go further, let's see where all the sets are. Each of the 3 rows is a set. Each of the 3 columns is a set. Are there any other sets? Yes. For example, these 3. I'll call them up diagonals. The yellow up diagonal is broken in 2 parts because it hit the boundary of our diagram. It wraps around. Same for the blue up diagonal. These 3 up diagonals are sets. Are there any other sets? Yes, these 3 down diagonals. These 4 directions give all the sets. By the uniqueness principle, every pair of cards is in exactly one set. So every pair of cards is on the same row, column, up diagonal, or down diagonal. That's a key point. Here's a geometric view. We've shrunk each card to a point. Here are the 3 rows. Here are the 3 columns. Here are the 3 up diagonals. Some of the lines wrap around. And here are the 3 down diagonals. Every set is a line, possibly with wraparound. Okay, back to counting. We have 5 cards, say these. We already counted 10 pairs among these 5 cards, but we're looking for a second way of counting the pairs. Let's see which direction our 5 cards are in. For example, how many cards are in each row? Well, there are 2 cards in the first row, 2 cards in the second row, and 1 card in the third row. And that's about the only thing that can happen. We can't have 3 cards in the same row because each row is a set, and we assumed our 5 cards don't have any sets. Instead of a 2-2-1 split, we could have a 2-1-2 split or a 1-2-2 split, but for counting purposes, those splits are the same. With our 5 cards distributed like this, how many pairs of them are on the same row? Well, there is 1 pair on the first row, 1 pair on the second row, and 0 pairs on the third row. Altogether, our 5 cards have 2 pairs on the same row. That's counting by rows. We can do the same thing for columns. We have 5 cards like these. They have a 2-2-1 split. So among our 5 cards, 2 pairs will be on the same column. We just looked in the row and column directions. Next, let's look at the up diagonals. Here they are. By the same reasoning as before, our 5 cards have 2 pairs on the same up diagonal. Finally, we can look at the down diagonals. By the same reasoning, our 5 cards have 2 pairs on the same down diagonal. Okay, let's combine everything we've learned into one key visual. It's called an incidence graph. We have 5 cards, so 10 pairs. I've listed the 10 pairs on the left. On the right, I've listed the 4 directions. We'll draw an edge between a given pair and a given direction if that pair of cards lies in that direction. For instance, there's an edge between pair 1 and columns because in this example, the first pair of cards are in the same column. By the uniqueness principle, every pair of cards are in exactly one set. So on the left, every pair has exactly one edge coming out of it. Among our 5 cards, supposedly without any sets, we already figured out that 2 pairs of them will be in the same row. So we'll have 2 edges coming out of rows. The same is true for columns, up diagonals, and down diagonals. Okay, let's count the number of edges in the diagram in 2 ways. From the left, the number of edges is 10 times 1, which is 10. From the right, the number of edges is 4 times 2, which is 8. What's that mean? Contradiction. The number of edges can't be 8 and 10. So our assumption that our 5 cards don't have any sets must be false. 5 cards must have a set. Let's give a recap of two-dimensional set. We found 4 cards without a set. We just showed that 5 cards must have a set. So 4 cards are the most without a set. Yay! Okay, that was 2 dimensions. Are you ready for 3 dimensions? Here we can use any color, but the only shading is solid. There are 27 such cards. What's the most number of cards we can have without a set? Let's try to use 4 cards from the red box, as in 2 dimensions. We can do the same for the green box. That gives us 8 cards. But now we're stuck. We can't extend this example. Does that mean the answer is 8? Remember, we have a choice in which 4 cards to choose. For example, we can choose these 4 cards in the green box, like this. Now we can choose a card in the purple box. Altogether, we have 9 cards. Is that the extreme example? Yes. In 3 dimensions, 9 cards are the most without a set. We'll prove that 10 cards must have a set. How shall we do so? We'll again use a proof by contradiction. Assume there are 10 cards without a set. We'll reach a contradiction. As before, we'll count pairs. Here are 10 cards. How many pairs of cards are there? I don't feel like counting all these edges, but combinatorics shows us how to count without counting. The number of pairs is 10 choose 2, which is 45. Next, let's see where our 10 cards, supposedly without a set, could be. How many cards will be in each of the 3 boxes? Could we have 5 cards in the red box? No. By our 2-dimensional result, 5 cards would contain a set. So there are at most 4 cards in the red box. The same is true for the purple box and the green box. Okay, what's a possible split? We could have 4 reds, 4 purples, and 2 greens. Are there any other possibilities? Yes. we could have 4 reds, 3 purples, and 3 greens. Those are the only 2 possibilities, except for reorderings. So let's analyze those 2 cases. In case 1, we have a 4-4-2 split. How many pairs will we have in the same box? We have 6 red pairs, because 4 choose 2 is 6. Similarly, we have 6 purple pairs. Finally, we have 1 green pair. Altogether, we have 13 same box pairs among our 10 cards. Let's do the same analysis for case 2. We have a 4-3-3 split. That means 6 red pairs, 3 purple pairs, and 3 green pairs. Altogether, we have 12 same box pairs among our 10 cards. Let's put both cases together. We have either 12 or 13 same box pairs among our 10 cards. That was splitting our cards by color. 3 colors, each with 9 cards. But we can split our cards in other ways too. Remember, in 2 dimensions, we split our cards in 4 different directions: rows, columns, up diagonals, and down diagonals. How many directions are there in 3 dimensions? Well, think about this question geometrically. First, let's begin with a basic question. Suppose we fix one of our cards, say this purple card in the middle. How many sets contain that particular card? Well, we can enumerate the sets. Here they are. There are 13 sets. Is there a slick way to see why the answer was 13? Yes. We have 27 cards. Ignoring the starting card, we have 26 remaining cards. We can choose any of them to be the second card in the set. Say we choose this card. By the uniqueness principle, that determines the third card of the set. Does that mean there are 26 sets containing the starting card? No, because we could have chosen the second and third card in either order, so we have to divide by 2. There are indeed 13 sets that contain a given card. Let's think about what we just did geometrically. Here's a 3-dimensional cube. Each of the 27 points represents a different set card. I've colored the points red, purple, and green to remind you of set. Every card is a point. What does a set correspond to? It will be a line in space. Here's one example. The 3 points on this line correspond to a set. Given a line like this, going through, say, the middle point, how can we split the points into 3 parts? We can draw planes perpendicular to this line. For example, here's one plane. I made the 9 points on this plane bigger so that you can see them. Here's another plane, and here's a third plane. Altogether, we get 3 parallel planes. This concept is important enough that we'll give it a name, a triplane. A triplane is a family of 3 parallel planes. Each plane contains 9 of our points, 9 of our cards. All 3 planes have the same orientation. That was one example of a triplane. Let's look at another example. This time I'll start with a diagonal line. What are the planes perpendicular to it? Here's one plane. Here's another plane. Notice that this plane is broken. It wraps around when it hits the boundary of the cube. And here's a third plane. Altogether, we get another triplane. That's looking geometrically, but we can do the same thing to our set cards. Here's the same triplane shown on cards. I've colored one plane pink, another plane yellow, and a third plane blue. How many triplanes are there? Remember that a triplane was determined by a line through the middle point. And we already found that the number of lines, the number of sets, going through a given point, a given card, is 13. So there are 13 triplanes. Here they are, each one a family of 3 parallel planes. Now we can generalize something we said before. Remember, we have 10 cards, supposedly without a set. Before we said that there are 12 or 13 pairs of our 10 cards that have the same card color, red, purple, or green. That holds for any given triplane. The number of pairs of our 10 cards that belong to the same plane of a given triplane is either 12 or 13. We're nearly ready to derive a contradiction. We just need one more count. Here's our cube again. Suppose we pick 2 of the points, which I've made bigger. How many of our planes contain these 2 points? Well, containing these 2 points is the same as containing the line. And we can draw all of our planes that contain this line. Here they are. There are 4 of them. Every pair of our points belongs to exactly 4 of our planes. Okay, now we're ready to finish off the 3-dimensional question. To do so, we'll use another incidence graph. Remember, we have 10 cards, supposedly without a set. How many pairs are there of 10 cards? We already counted that there are 10 choose 2 of them, 45 pairs. I've listed them on the left. On the right, I've listed our 13 triplanes. We'll draw an edge between a given pair and a given triplane if that pair of cards, that pair of points, belongs to the same plane of the triplane. We'll get a graph that looks something like this. For each of the 45 pairs on the left, how many edges touch it? There will be 4, because we just counted 4 planes through every pair of points. That will tell us how many edges there are. The number of edges will be 45 times 4, or 180. Great. Now let's count in another way. For each of the triplanes on the right, how many edges touch it? We already determined that the answer is either 12 or 13. So the number of edges is at most 13 times 13, or 169. On one hand, the number of edges is 180. On the other hand, the number of edges is at most 169. What's that mean? Contradiction. Our assumption that there are 10 cards without a set is false. So we've finally finished 3-dimensional set. The maximum number of cards without a set is exactly 9. Super! That was 3 dimensions. Are you ready to travel to the 4th dimension? Here's the standard version of set. There are 81 cards. What's the largest number of cards we can have without a set? For the cards on top, we can choose 9 cards, as in the 3-dimensional version. We can do the same for the cards on the bottom. That gives us 18 cards. But now we seem to be stuck. Is 18 the largest? For the cards on the bottom, we can reverse the choice like this. Now we can pick up a card in the middle row, like this. We can even pick up another card in the middle, like this. We now have 20 cards. We're stuck again. Is 20 the maximum? Yes. We'll prove that 21 cards must have a set. Assume there are 21 cards without a set. We'll derive a contradiction like before. First, among 21 cards, how many pairs are there? The answer is 21 choose 2, which is 210. Next, let's figure out where the 21 cards could be. We'll think of the 81 cards as divided into 3 bands, namely the top band, the solid cards, the middle band, the striped cards, and the bottom band, the cards with empty shading. How many cards can go into each band? There are at most 9 cards in each band. Why? Because we already showed that in 3 dimensions, there are at most 9 cards without a set. So, how can we split 21 into 3 parts, with each part being at most 9? There are a bunch of cases. We could have a 9-9-3 split, a 9-8-4 split, a 9-7-5 split, a 9-6-6 split, an 8-8-5 split, an 8-7-6 split, and finally, a 7-7-7 split. There are 7 cases in all. Here are all 7 cases in one place. Just like in lower dimensions, we can count the number of pairs in each case. Let's look at the 9-9-3 split for our 21 cards. In the top band, there will be 36 pairs of our cards, because 9 choose 2 is 36. Similarly, the middle band will have 36 pairs. The bottom band will have only 3 pairs. Altogether, this case has 75 pairs of cards in the same band. We can do the same analysis for the other cases. Case 2 has 70 pairs of cards in the same band. Case 3 has 67 pairs. case 4 has 66 pairs. Case 5 also has 66 pairs. Case 6 has 64 pairs. Finally, case 7 has 63 pairs. Let's summarize these counts. We have 21 cards, supposedly without a set. There are 7 cases for how they can be split into 3 bands. For each case, here are the number of pairs in the same band. In every case, the number of such pairs is between 63 and 75. From here, we could try to derive a contradiction like we did before. Unfortunately, we won't get a contradiction using just pair information. We need to go beyond pairs. What is beyond pairs? How about triples? When I say a triple, I don't necessarily mean a set. In fact, it won't be a set because we assumed our 21 cards don't have any set. First, a question about triples. Among our 21 cards, how many triples are there? The answer is 21 choose 3, which works out to 1,330. For comparison, the number of pairs is 210. Okay, let's go back to our 7 cases, counting the number of triples in the same band. Here's case 1. In the top band, there are 84 triples, because 9 choose 3 is 84. Same for the middle band. The bottom band has just 1 triple. Altogether, there are 169 triples in the same band. We'll do the same for the other cases. In case 2, there are 144 triples in the same band. Case 3 has 129 same band triples. Case 4 has 124 triples. Case 5 has 122 triples. Case 6 has 111 triples. Finally, case 7 has 105 triples. Let's summarize these numbers. We have 21 cards, supposedly without a set. There are 7 ways to split them up into 3 bands. Here are the number of pairs and the number of triples in each case. It's hard to see what's going on with this data. What should we do? Let's plot the data. Here's a graph of the 7 cases. The horizontal axis is for the number of pairs. The vertical axis is for the number of triples. I've drawn 1 point for each case. I've written the coordinates of the 2 extreme points. The data points look vaguely on a line, but not exactly. Let's draw the line through the 2 extreme points. The other 5 points are a little above this line. We know the coordinates of the 2 extreme points, so we can find an equation of the line. Here it is. The other 5 points are above the line, so they satisfy this strict inequality. To combine all 7 cases, we can use a less than or equal to sign. Remember that inequality because we'll use it later. For now, though, let's go back to thinking geometrically. Here are the 81 cards of set, represented as 81 points in 4-dimensional space. I can't draw a 4-dimensional cube, so instead I've drawn 3 slices of a 4-dimensional cube, each slice being a 3-dimensional cube. What does a set look like? For example, here's a typical set of 3 cards in yellow. In space, the set looks like a line going through 3 points. Given a line, we can consider the hyperplanes perpendicular to that line. A hyperplane is a 3-dimensional slice of the 4-dimensional space. For this yellow line, there are 3 relevant hyperplanes perpendicular to it, 1 for each point on the line. In other words, we get a tri-hyperplane. I can't easily draw those hyperplanes, but I can show you them on the set cards. Here they are. The yellow cards are on 1 hyperplane, the blue cards are another, and the pink cards are a 3rd hyperplane. We have a tri-hyperplane. Each hyperplane contains 27 cards. To continue, we'll need to count hyperplanes. To start, we'll look at this question. Given a card, say this middle card, how many sets contain it? We have 80 choices for the second card, which determines the third card. The second and third cards can go in either order, so the number of sets containing the given card is 40. In the 4-dimensional cube, that means the number of lines going through the middle point is 40. Each such line determines a trihyperplane, perpendicular to the line. So, how many trihyperplanes are there? Also 40. Next, another counting question. Given a pair of points, how many hyperplanes contain that pair of points? For example, here I have a big green point and a big red point. How many hyperplanes contain them? That's the same as the number of hyperplanes that contain this yellow line. What's happening on the top layer, the middle layer, and the bottom layer is the same. So we can reduce the question by one dimension. Back in 3 dimensions, we already counted that the number of planes that contain a given point is 13. So in 4 dimensions, the number of hyperplanes that contain a given pair of points is also 13. One final counting question. Given a triple of points, how many hyperplanes contain all 3 of those points? For example, here's a big green point, a big purple point, and a big red point. I purposely chose them not to be on the same line. For a hyperplane to contain these 3 points, it must contain this plane. And again, we can reduce the counting by one dimension. In 3 dimensions, we already counted that the number of planes that contain a given pair of points is 4. And so in 4 dimensions, given 3 points, not all on the same line, the number of hyperplanes that contain all 3 points is also 4. Let's summarize the 3 counts we just came up with in 4 dimensions. Given a point, the number of hyperplanes containing that point is 40. Given a pair of points, the number of hyperplanes containing that pair is 13. Given a triple of points, not all on the same line, the number of hyperplanes containing that triple is 4. Note that all 3 counts involve a power of 3. Remember those counts. Okay, let's try to derive a contradiction. Here's an incidence graph again. Remember, we have 21 cards, supposedly without a set. The number of pairs of cards is 21 choose 2, which is 210. We just counted the number of trihyperplanes as 40. We draw an edge between a given pair and a given trihyperplane if the 2 cards, the 2 points, lie on the same hyperplane of the given trihyperplane. That's for pairs. We'll draw an incidence graph for triples too. The number of triples of cards is 21 choose 3, which is 1,330. We draw an edge between a given triple and a given trihyperplane if the 3 cards, the 3 points, lie on the same hyperplane of the trihyperplane. How many edges come out of every pair? 13. How many edges come out of every triple? 4. We just figured out those hyperplane counts. Next, let's count edges. The number of yellow edges is 210 times 13, which is 2,730. The number of blue edges is 1,330 times 4, which is 5,320. Now we'll count edges in another way. Let's look at each trihyperplane. For example, focus on trihyperplane 1. Let's call P the number of yellow edges coming out of it, and T the number of blue edges coming out of it. Here P stands for pairs and T stands for triples. We had 7 cases for what P and T could be, but each case satisfied this inequality. We can add up 40 such inequalities, one for each trihyperplane. We'll get this inequality. But we already know the number of yellow edges and the number of blue edges. Let's plug in their values and simplify. And so we've reached a Wait a minute, that's not a contradiction. It's a true inequality. Was this a waste of time? Not really. If any of the inequalities along the way were a strict inequality, then this would be a strict less than, and that would be a contradiction. Let's go back to our 7 cases. We have 21 cards, supposedly without a set. There are 7 possible cases for how they can be distributed among the 3 hyperplanes. In the first and last case, we had this equation, but in the middle 5 cases, we had a strict inequality. We can't have a strict inequality because that would lead to a contradiction. So we're left with only two cases. As a bonus, we no longer need triples. Two cases is much better. Even better would be one case. But how can we do that? After all, 75 and 63 are different. Or are they? Let me ask you a little question. Suppose it's 12 o'clock. We won't care whether it's AM or PM. 63 hours later, what time will it be? It'll be 3 o'clock. 63 is 3 mod 12. Let's go back to 12 o'clock again. 75 hours later, what time will it be? Also 3 o'clock. 75 is 3 mod 12. In other words, 63 and 75 are the same mod 12. We've reduced our two cases to one. Okay, back to our incidence graph. Let's start with the hyperplanes. We know that each trihyperplane contains either 63 or 75 edges. In other words, the number of edges coming out of each trihyperplane is 3 mod 12. That means the number of edges is 40 times 3 mod 12, which is 0 mod 12. On the other hand, by starting from the pairs, we know that the number of edges is 210 times 13. When we work that out mod 12, we see that it is 6 mod 12. The number of edges is both 0 mod 12 and 6 mod 12. What's that mean? Contradiction. Yay! Our assumption that there are 21 cards without a set is false. So the maximum number of cards without a set is 20. We did it! We've solved the question in 2 dimensions, 3 dimensions, and 4 dimensions. What about higher dimensions? For example, 5-dimensional set, sometimes called megaset. Here we'll need a 5th feature, such as a background color. How many cards are there in 5-dimensional set? It's 3 to the 5th, which is 243. What's the maximum number of cards without a set? The answer turns out to be 45. The proof uses Fourier transforms along with a computer search. How about 6-dimensional set? The number of cards is 729. What's the maximum number of cards without a set? The answer turns out to be 112. The proof uses combinatorial casework along with a computer search. And how about 7-dimensional set? The number of cards is 2,187. What's the maximum number of cards without a set? No one knows. As far as I'm aware, the answer is between 236 and 292, but no one knows better than that. Maybe you can improve on one of these bounds. As I mentioned at the beginning of the video, in 2016, there was a breakthrough in high-dimensional set. Think of the dimension as being 100 or more. In n dimensions, the number of cards is exactly 3 to the n. What's the maximum number of cards without a set? The breakthrough was to show that the number of such cards is at most 2.7552 to the n. The important thing is that the base, 2.7552, is strictly less than 3. Before that breakthrough, it was conceivable that the number of cards without a set could be fairly close to 3 to the n. This result was due to Jordan Ellenberg and Dion Geisweit. How about lower bounds? Here's a recent result. Google DeepMind has constructed a collection of at least 2.2202 to the n cards, at least for n large enough. I said DeepMind, but actually it was collaboration between DeepMind and Jordan Ellenberg, who was part of the previous breakthrough. It was a human-machine interaction, with each needing the other. I don't have time to prove these high-dimensional results here, but even in our analysis of standard set in 4 dimensions, we encountered so many fascinating concepts in discrete math. If you'd like to check your understanding, I created a sequence of combinatorial exercises for set. I placed a link to the document in the video description. If you like this video, you'll enjoy this other one too. Thanks for watching!